So I want to give you a little hint on how to attack number 46 from lesson 2-3. This is similar to one of our homework assignment problems from WebAssign. This problem has to do with oxygen consumption, comparing walking and running. And notice it tells us that oxygen consumption is measured with millimeters per pound per minute. That's the units of measure for that particular measurement, that quantity. Now this first function has to do with walking. And the function for walking at particular speeds, miles per hour, x miles per hour, is estimated by this quadratic, 5/3 x squared plus 5/3 x plus 10. Now for a runner, that function is a linear function. Again, x is measured in miles per hour. If you input the speed, it'll calculate the oxygen consumption. You take the speed, you multiply by 11, and you add 10. Here you take the speed, you square it, you multiply by 5/3, then you add on the speed times 5/3 again, plus 10. So we have these two functions, and the first thing we're asked to do is to sketch graphs, okay, of f and g. Well, you could do that. You could kind of fumble your way through that with a piece of graph paper, but we know that we have tools that can help us with these graphs. So I'm going to go ahead and utilize one of those right now. Keep in mind that for the walker, this function applies for the domain where x is between 0 and 9. But for running, the function only applies from 4 to 9. Okay? So it's not the entire graph. So let's use Desmos graphing calculator to help us draw these pictures. So what I've done is I've gone ahead and I've entered the two functions in Desmos. The quadratic function, which is the red one, is for the walker. So red is for the walker. And the blue function is the linear function, and that is the runner. Now the blue function is only valid from 4 to 9. So that particular function, the piece that we're graphing, is actually just this piece here, from x equals 4 to x equals 9. The function for the walker, however, is valid from 0 to 9. So it's basically the entire quadratic that is shown here. So as you're choosing your graphs, keep in mind that the linear function is only valid from 4 to 9, but the quadratic is valid from 0 to 9, from x equals 0 to x equals 9 out here. Okay? So those are the two pieces of the graph. If you're sketching the two functions, this is what they would look like. Since they're on a closed interval, we can begin and end them on the left and right with solid dots. Now in part B, we're asked to find the speed for which the oxygen consumption is the same for the walker and the runner. And when we say the same, that means set these two equations equal to each other, these two expressions. So you can see I've done that here. And then we're going to want to solve these. So the first thing you'll notice is if I subtract 10 from both sides, these 10s cancel out. And that leaves me with 5/3 x squared plus 5/3 x equals 11x. And this can be an intimidating function because fractions are involved in these coefficients. Not everybody's real comfortable with that. And so what I often like to do is just eliminate the fractions. In this case, an easy way to eliminate these fractions is just to multiply the whole expression, the whole equation, by 3. Basically, I multiply both sides by 3. When you do that, these 3's here will cancel, and I'll simply have 5x squared plus 5x on this side, and then over here 3 times 11 is 33, so that's 33x. Then I can just make a simple quadratic by subtracting 33 from both sides, 33x I should say, and I get something like 5x squared plus minus, 5x squared minus 28x. And that'll equal 0. and this is a quadratic. I can factor it. Simply factor the x out, and I get 5x minus 28 equals 0. The solutions here are either x equals 0, right, or 5x minus 28 equals 0. X equals 0 doesn't make a lot of sense. That means we're not moving, we're not running or walking. So I'm going to throw that one out. And now I simply need to solve 5x minus 28 equals 0. And I'll leave that up to you, but it looks like it's going to be around 5.6. And if you want to use your graph to verify what we just found, I think you'll agree that this place where these graphs cross is right about there, and it is in the 5.6 range. So that's a reasonable answer. Letter C from the problem asks us what happens for speeds beyond that point. And what you'll notice is that the graph of the walker is higher than the graph of the runner. So as the speeds pass the 5.6 mile an hour speed, all the speeds this way, the walker is actually consuming more oxygen than the runner. Basically, at speeds greater than 5.6 miles per hour, running is more efficient. There's a more efficient way of using your oxygen, which is interesting if you're into exercise and things like that. So for speeds slower than 5.6, you're going to be more efficient using your oxygen at walking speeds. But for speeds greater than 5.6, you're going to be more efficient, or consume less oxygen, I should say, running than you would walking. So that's kind of how to interpret that part C. If you're interested and you want to know what the oxygen consumption is right at the 5.6 mark, we simply need to plug that into either one of the functions to get the y value. It's going to be a little over 70, it looks like, in this range here. But you can just plug 5.6 into either function to get that value. So good luck with this problem.